So we completed chapter 1, 2, and 3, which is about descriptive statistics. We have learned how to collect, organize, and summarize data, and present it using a graph. That's descriptive statistic. The second part of statistic is inferential statistic, in which we try to generalize what we get from descriptive statistic to the whole population. In order to do this, we need probability. We are going to learn in chapter 4, 5, and 6 some basic probability theory. We will start with the definition of probability in chapter 4. Probability is essentially a measure of uncertainty. We have used the word probability in many cases. You can say it is possible that, like maybe, for example, if somebody asks you, are you going to play a sport tonight? You might say maybe. Somebody asks you, if you buy a lottery ticket, are you going to win? You will say maybe. If somebody asks you, are you going to have dinner tonight? You can also say maybe. We want to see that maybe is not clear enough. The maybe for winning the lottery is not the same as the maybe for eating dinner tonight. Both have something in common, is that it has not yet happened and we are not sure about it. But for one, we don't even think that you can win that jackpot, but you buy the lottery because you hope you can win. So there is a maybe that is very weak. For another one, like eating dinner tonight, unless something really happened, you will have to. So one is closer to an impossibility and another one is closer to a certainty. In between, there is so much that sometimes we may prefer to know. If you ask a friend, are you going to visit tonight? If the friend say maybe, you might want to have some more level of certainty on that. Can you give me a number associated to it? So the number that we associate to uncertainty is what we call probability. It is most of the time expressed in terms of percentage. For example, the weather tomorrow, it might tell us that there is 60% chance that it will snow, 30% chance of shower. Those numbers help us to make better decisions. If I just tell you that it will snow tomorrow, and when I say 30% chance and 70% chance is two different types of information. So we are going to learn how to calculate probability. First of all, we are going to look at the type of probability. Sometimes your probability is just based on how you feel. You can tell a friend that I'm 80% sure I will come. Or 30%. This is based on your intuition, how you feel. So, are you going to have dinner tonight? Yes. How sure? 100%. But something might happen and you cannot make it. We don't think about that happening anyway. But all of these are intuitive probabilities, which is essentially based on how you feel, based on intuition. Super Bowl is on Sunday. And if you ask somebody in Pittsburgh who is going to win, the person might not even care about it. But if you ask somebody in Florida, I will say, oh, the Tampa Bay are going to win. Okay, so that is just intuition. It's just feeling. And then we have empirical probability. In empirical probability, we use relative frequency. You remember relative frequency? When you divide from what you have had as a sample, you compute the relative frequency. If somebody wants to know the proportion of males on campus here, you might randomly select 100 people or 50 and take the proportion. That is a relative frequency. You can find out that there are 60% of female. And if somebody asks what is the probability that a randomly selected student is female, you might say 60% based on the random sample that you have. Just as people are taking COVID vaccine now, or what is the probability that it will work? They might say 90% or 95%. This is essentially based on a sample that was taken. It is empirical probability. It is not, it is empirical probability. It's based on a concrete experience. It uses relative frequency from a sample. For example, if you want to determine the probability that a coin that is tossed will be head or tail, you can decide to toss that coin 10 times, or 20 times, or 30 times, and count the number of heads. That is empirical probability. The issue with empirical probability is that it is not always the same, because it depends on the experience you have done. Let's look at an example of the use of empirical probability by simulating tossing a coin using Excel. I want to toss a coin here using Excel. That is a simulation. So I'm going to use 1 for head and 2 for tail and randomly pick one number out of the two. So I will say random between 1 and 2. So this is a random number between 1 and 2. If I want to replicate this 10 times, this is what I get. If 1 is for head and 2 is for tail, how many head do we get here? How many head? 1 is for head, 2 is for tail. We have 6 out of 10. I'm going to do it a second time. How many head do we get here? 7. So it is not exactly the same. There's an issue with empirical probability. I'm going to do it 20 times because I want to keep it large enough for you to see. Each time I do it here is going to adjust the first one. This is 20 times. Look at the first one again. How many head do we get? The first A, column A, how many head? 2, 2 out of 10. Column B, how many head? 2. So this is 4 out of 20 for 22s. So we can use this to determine if actually this procedure is providing us with a random number. We can use it to say, is this method of acting actually producing a simulation? We are going to learn that in chapter 7. Chapter 7 and 8, how what we get can be used to determine if the procedure is fair enough. So now I'm going to go, I will try again, and I will go 1 to 100. So now I'm going to say, if the number is even, it is head. If it is odd, then it is tail. Even for head, odd for tail. How many head? 6. Let's do the same thing here. How many head here? How many even number? How many even number here? 4. So how many even number are in C now? You know C has changed. How many even number are in C? 5. If we combine both to make it 20, how many even number are we going to get? 4 and 9. I'm sorry, 4 and 5. That makes 9. So this is empirical probability. You see that because we were choosing numbers from 1 to 100, we have a better result than when you are just choosing between 1 and 2. So all of those are involved. When you toss a coin, are you tossing it exactly the same each time? All of those matters for empirical probability. So now, in classical probability, we used the fact that there are 2 possibilities when you toss a coin, head or tail. One of the 2 is head, and we say the probability of getting head when you toss a coin fairly, and it's a fair coin, is 1 over 2. And that number does not change. So each time we are thinking about checking the fairness of an issue, we can use that half as a rule to determine how fair is the procedure we are using. So there are 3 types of probability: intuitive, empirical, and classical. So we are going to focus more on classical probability, but in some cases, we are going to be using empirical probability as well, like when you have a random sample. So the law of large number helps us to match empirical probability to classical probability, meaning that if you toss a coin 50 times, the number of heads will be closer to 25 than when you toss it 10 times to 5. That is, you get closer to half when you toss the coin more times. So in empirical probability, if the number of trials is large enough, your probability gets very close to the classical probability. Classical probability is based on what we call a random experiment or a probability experiment. In this experiment, you think about a situation and look towards the possibilities that you have. For example, winning lottery. You might say either you win or you don't. There could be in between, you can win $2, you can win $10, and all those. You can win a large amount or you don't win a large amount. So we can think about what are our options. So in classical probability, we think of a random experiment as an experiment in which you don't know what the outcome is going to be, but you know what it can be. You don't know whether you are going to win or not, but you know either you win or you lose. So if you are able, for example, when you toss a coin, you don't know whether you are getting head or tail, but you know either it's head or it is tail. When you roll a die, you don't know what number you are going to get, but you can know the possible numbers you can get. So the set of all possible outcomes of a random experiment or a probability experiment or a statistical experiment is called a sample space. So when you want to do probability, you want to know what is your sample space or what is the number of outcomes in the sample space. For example, when you toss a coin, as I say, you get head or tail. When you roll a die, you have 1, 2, 3, 4, 5, 6. When you toss a coin twice, you can have head, 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 tail, tail, head, tail, tail. If you think about picking a card from a deck of cards, you have 52 cards to pick from. You can list all of them. Can we list all those 52 cards? We know there are 4 types. You have diamond, you have spade, What else? Heart and which one? Club. Okay? So those are the 4 types. We should know those things because when I'm asking you a question about card, I assume that you know what cards are. Each of the type has how many cards? Each type, there are 52 and 4 types. So each type we have how many cards? Like club, how many clubs do we have? 13. 13 club, 13 diamond, 13 spade. So we have what is called face card. That is, there is a face on that card. In each type of card, how many cards are face cards? Like if you take diamond, how many of the diamond have a face? A human face. Three or four? Do you have 4 faces or 3? 3 faces. We want to agree on that. We are not counting ace as a face card, okay? We are not counting. If I ask you what is the probability that the card is a face, I am thinking about king, queen, or jack. We want to agree on that. So in classical probability, once you have your sample space, which is all possible outcome, the probability of any event, an event is any portion of the sample space. The probability of an event is the number of outcomes in that event divided by the total number of outcomes. It's just like relative frequency, but now it's about events. If I roll a die, for example, I have 6 possible numbers in the sample space. If I want the probability that my number is less than 3, there are 2. So the probability will be 2 divided by 6. Okay? There are 2 special types of events. An event with no outcome is the impossible event. The whole sample space is an event too, which is called a certain event. So the probability is a number between 0 and 1. For impossible, the probability is 0. For the certain event, the probability is 1. It can also be expressed as a percentage. For example, when you toss a coin, what is the probability of getting head? We say it was 1/2. If we roll 2 dice, what is the probability that the sum of the 2 dice is 3? If we roll 2 dice, we can represent the outcome on a table like this. So each side is a die. So each cell here is an outcome. How many outcomes do you think we can have here when you combine 2 dice? Each of these cells is an outcome. How many do we have? How many outcomes do we think we will have? Anybody? Just count here. 36. We have 6 on each side. That makes 36. So what is the probability that the sum of the number is 3? What is the probability that the sum of the number, the two numbers, has a sum of 3? Two over 36. Do you see that there are two outcomes with a sum of 3? What is the probability that the sum of the two numbers will be 1? 0 is an impossible event. The sum is more than 1. The sum is more than 1. For the sum to be more than 1, all the sums are more than 1. Is the certain event with probability 1. Another example is tossing a coin 3 times. When we toss a coin 3 times, yeah, the first time you can get either head or tail. So the first time, head or tail. The second time, head or tail. If the first time was head, second time will be head or tail. Head or tail. So for each time, we prolong the tree with the two options. So now the branches are going to produce the outcome. Head, head, tail. Head, tail, head. Head, tail, tail. Tail, head, head. Tail, head, tail. Tail, tail, head. So how many outcomes do we have? How many? 8 outcomes. What is the probability that we will get exactly 2 heads? Exactly 2 heads. We have this 2, this 2. Do we have more? Exactly 2 heads. 3 over 8. So in a probability, you want to know what is the sample space. You can use the sample space to determine the number of possible outcomes and then count for the events that you have the quotient to find the probability. In probability, there is an important rule, which is the complement rule. The complement is what is missing to make it complete. Everything which is not in the event is in the complement. So for example, if some students were not here, we will say the complement of the students who are present are those who are absent. So when you combine the event with its complement, you get the entire sample space. So for that reason, the complement rule is probability of the complement is 1 minus probability of the event. For example, if there is 30% chance that it will rain this evening, what is the probability that it will not rain this evening? 30% chance that it will rain, what is the probability that it will not rain? 70%. You just do 1 minus the probability. It will become useful. For example, if we want to know here, a coin is tossed 3 times, what is the probability that at least one head, we have at least one head? At least one head. We are going to say that if E is at least 1, if E is at least 1 head, then what will be E complement? The opposite of at least 1 head is no head. No head. So how many outcomes have no head here? How many outcomes have no head? 1. So the probability of E complement will be 1 over A. And the probability of E will be minus 1 over A. That is an example of the use of the complement rule. We are going to use it a lot in the future. Whenever we hear of at least, if you take the complement, it will be not. So you want to, that was section 1. Essentially, you want to know that a probability experiment leads to the sample space. An event is any portion of that sample space. The probability of an event is the number of outcomes in the event divided by the number of outcomes in the sample space. So most of the time, we are going to be dealing with a combination of events. In that combination, we use the expression or and on to combine event A and B. So A or B are outcomes that are either in A or in B or in both. A and B are outcomes that are at the same time in A and in B. Let's take the example of a deck of cards. How many cards are diamond? How many cards are diamond? 13 cards are diamond. How many cards are aces? 4. How many cards are either diamond or face? I'm sorry, or ace. Either diamond or ace. How many? Either diamond or ace. Okay, what number now? Think everybody. 16. Wow, that's great. Why didn't we say 17? Because there is ace in both. So when you are counting the 13 diamond, it has already 1 ace. So there are 4 aces, only 3 are needed. So that takes us to what we will call the probability rule for addition. So, the number of outcomes that is A or B is equal to the number of outcomes and the number of outcomes and the number of outcomes. If you don't subtract this, you are going to count it twice in if there are outcomes. No. When there is no outcome, A, B are mutually exclusive. With A and B. For example, if I want a car that is at the same time king and queen, it's impossible. If I want a student who is at the same time male and female, is it possible? Male and female? For probability, no. Right? I want us to agree on what we will be doing. Whenever I write male and female, don't say or not. So, we are still going to wait until science improves well enough for male to be and I'm trying to say not a controversy. When a male becomes female and a male wants to go and compete with females, no, it's not good, right? There's some cheating. I'm sorry if you don't agree with me, but I believe there is some cheating somewhere. Science cannot prove it, but it's not fair. You know, if I am a man, I will not be happy to see that when girls are running, one of them, who is actually a boy, is also running. So sometimes, even if you don't want to be fair, just try to be fair small. Okay? To accept that, okay, on my unfairness, I want to be fair. I don't know whether that's possible. Okay. Otherwise, all the other girls, don't think about university students. Think about girls that just want to pray. You will be frustrated. Would you like that? No. This is a little politics, I know. So, but in probability, we are still going to be dealing as if we are still in those old days. Whenever we say boys and girls cannot be known before birth, we accept like that. Because that one we know we can know. But before, you know, when a woman was expecting a child, nobody knows whether it was a boy or a girl. When you say it's a boy, everybody's happy. When you say it's a girl, everybody's happy. Don't you think people were happier? They had more reason to be happy than we have today. Anyway, let's do statistics. Suppose we have two events here of a sample space of numbers 1, 2, 3, 4, 5, 6. Then A is 1, 3, 5, and B is 2, 3, 5. Is there any outcome in common to A and B? What are the outcomes for A and B? A and B. It is in A and it is in B here. A and B will be, because I am explaining this, it looks easy, but sometimes students think A and, because even when people are speaking, that's what they think about. Or is what people consider as their and. So now A or B is either A or B. So we will take 1. This is A or B. So let's look at this example. Student club at a small college is made up of junior and senior students. There are 13 juniors and 15 seniors. 8 of the senior students are female. If there are 11 males in the club, find the probability that a randomly selected member of the club is. So to answer this type of question where you have category that could overlap, you make a contingency table. The contingency table, we put on one side events that are mutually exclusive and complementary. And here, so for example, we are going to say male and female. And here junior and senior. How many of the students are junior in the club? How many are senior? So any other information we get from there? seniors are female, so we write 8 here. Any other information? Look at any number that we have not used yet. 11 males. We put it here, the total of males. So based on this, what number should we put here? 15 senior, 8 females. How many seniors are male? And here? And here? And here? And total. You will know that you are making a mistake if you add this one is this and it's not the same as this. So this is how we can use a contingency table to put together information on a certain type of problems. So what is the probability that a randomly selected student from this club is female? Here we are using empirical probability, that is relative frequency. We have a sample of 28 students. What is the probability that a randomly selected student? So this club has 28 students. So you randomly pick one. What is the probability that that person is a female? What is the probability that the person is, let's just do junior? Junior. How many juniors? Out of. Now, female and junior. What will be female and junior? 9/28. We are learning how to read this kind of table. Okay. So now, probability of female or junior. And the probability of female will be number of female or junior divided by sample space. This number of female plus number of junior minus number of female. You could write it as probability as well. So as probability will be probability of female 70 plus junior 30 minus I. So what does this give us? 30 minus 9. You can divide both sides by 7. So that is all, using all. Now, suppose you know that the student is female. You know that it is a female student. What is the probability that that student is junior? What I'm asking here is probability that the student is junior given the student is female. Can somebody just try this? You know the student is female for some reason. You want to know whether the student is, what's the probability that that female student is junior? Any guess or any attempt here? So yes, 9/17. Because you already know that you are only dealing with females, that becomes like your total. This is called conditional probability. Conditional probability. I'm kind of hesitating whether I should continue with that or. I think we should leave this until after exam. I don't want to go too much. Yeah. So I want to quickly discuss about the project. Since we still have some time, just 5 minutes. So you already know that you are supposed to be in group for the project. If by the end of this week, you have not told me who you want to work with, I will just put you in a group and we still have 2 weeks, about 2 weeks. So, but I want us to be prepared for that. What I do, I just randomly distribute you. I just ask Canvas to put you randomly. But if you have preference, let me know. So 2 to 4 students in a group. At least 2, at most 4. You have 2 options. Either you choose to do A or you choose to do B. Most of the time, students choose option A. In option A, you are going to collect 30 data values. Evidence for collection of this data is listing them. Don't just assume that I know them. You list all the values, and then you organize them into a frequency distribution table. You will group them, use at least 5 or at most 8 group classes. You are going to show me how you got the width and use it to make class limits, class boundaries, class midpoint, frequency, cumulative frequency. I want at least those 5 categories. Class limits, class boundaries, class midpoint, frequency, cumulative. If you forget, think about your take-home problem. With the data, choose quantitative, please. Choose quantitative data, numbers that you can add and subtract so that you can be able to group. You can decide that you want to find out, for example, anything. How long do you spend sleeping every day or every week? Don't use that one, but as just as an example, you will get more. How many hours of television do you watch? How many friends do you have in Facebook, for example? You can be creative, think about any number, but get numbers. Group them into classes. If your numbers are maybe, for example, if you ask, how many siblings do you have? Now you might have 1, 2, 3, up to 5. You might not need to group that one, but you should know that you can also make class boundaries. One will be 0.5 to 1.5. Subtract 0.5, add 0.5 if you have single values. But I don't wish that you do that, but if you have to do that, that's what will happen. Then, organize into a frequency distribution table, present using a graph. Because these are quantitative data, I want you to use histogram. Then use Excel to present a statistical summary. That means use Excel to do chapter 3. You put your data, you know how we did it. Put your data and then compute the mean, the mode, the median, the standard deviation, the variance. That table that you get on Excel, you get it, you copy it and paste it on your project. And we know that you got it from Excel. Then, second part of it, this is second part of option A. Tell us the reason why you choose this topic. And who did what of each of you in the project. Maybe James collected data, or we each collected 10 data, and then James did the grouping or the histogram, and then Paul did the frequency distribution table, and Donna did the data summary, or we did it all together. I want you to just give me a brief summary how you work together to bring out the common project. And then Joseph was never coming, for example. So, because in project 2, you might now say, we were able to convince Joseph, now he's participating. So, what have you learned from your project that you wish others should know? In this, I want you to include the nature of the distribution. You are going to tell this from your histogram. You might be able to tell that it is symmetric, skewed to the left, or skewed to the right. It might not be any of the three. So you might say it is not symmetric and it is not skewed. You might observe that the mean is less than the median, or the mode is less than the median. Just tell me something. That is it for option A, choice A. Choice B, if you want, you go online. Online, you are supposed not to get me data for less than 50. Because sometimes you can have hundreds and thousands if you go on some site that have data. But it's the use of the data. So you do that if you are able to produce a histogram from that data, if you are able to make a time series graph, for example, from those data. So I am not encouraging you to do that, but if you feel like doing that, it is fine. What proportion of the values is within 2 standard deviation, and is it consistent with, and write a brief report. So I expect most of you to do option A, and if you are 4, make 40 values. Because each of you can collect 10 and you put it together. Okay. As you are sanitizing, I will quickly take the attendance. Everybody is here.